Hello and welcome to another Common Core Geometry video by eMathInstruction. My name is Kirk Weiler and today we'll be doing unit number 10, lesson number 4 on the area of a circle. Like many of the topics in this unit, this is a topic or a piece of it that you've seen before. You know, you've obviously seen the area formula for a circle and you've used it before. What we'll be seeing in this lesson is some applications of that formula that you may have to bring in other pieces of geometry that we've worked with this year. And then the second piece of it is we'll actually look at where that formula comes from. We'll try to get a sense for why the area formula for a circle is the way it is. All right, let's jump right into it though, and let's review that formula, right? So the area of a circle is always given by the number pi times the square of the radius's length, right? So pi r squared. And oftentimes, when you even ask a student what is the formula or the equation of a circle, they'll say pi r squared, just immediately, right? Where actually the equation of a circle is, something more like x squared plus y squared equals r squared. And we're going to jump into that, in fact, in the first exercise. So let's get right to it. Exercise number 1. For the circle whose equation is x minus 2 squared plus y plus 5 squared equals 36, which of the following is closest to its area? All right. So, it's simple enough. The area formula is right here, pi r squared. We've got the circle right here. Pause the video now. You might need to use your calculator on this and try to figure out which of these 4 answers is closest to the area of that circle. All right, well obviously the area formula of a circle depends on only one thing, and that's the radius of the circle. If we know the radius, we can calculate the area, right? So the question is, if we've got this circle, what is its radius? Well, we should know from previous work in the last unit that this is the square of the radius. So r squared is 36, which means r is the square root of 36, or just 6. Okay, so we've got the radius. In fact, what we really needed actually more than the radius was that number, the 36, because the area now is pi times the radius squared, so that's pi times 6 squared, or 36 times pi. Now, of course, if 36 times pi is one of the answers sitting here, we simply circle it and we write it down. But 36 times pi is a number all in and of itself, and we really need to use our calculators to figure out what that is. So I'm going to exit out of this really quick, jump into my Texas Instruments calculator, or I'm going to try to. Come on, there we go. And of course, all I need to do is type in 36 pi, right? Enter. And there's our area expressed as a decimal, 113.097, etc., right? Very, very close to 113. And there it is, choice 4. All right, so simple enough. Very often, the area of a circle is left in terms of pi, but of course, in most practical senses, when we actually need to have the area in some real way, we would want to do that multiplication, 36 times pi, and get an answer that we can use, like 113 square feet, square inches, square centimeters, whatever the units are that we're dealing with. All right, but ultimately speaking, keep in mind to use the area formula of a circle, you simply need to have its radius. And once you have it, pi times r squared. So let's keep going and take a look at another problem. Here we go. Exercise number 2. In this one, we've got a combination of shapes, and of course, they're going to ask us something about area. Here we go. A shape is constructed from a rectangle whose length is 10 inches and whose width is 8 inches, along with a semicircle attached at the end. What is the total area of this shape? All right, so I want the total area of this shape. Okay, you obviously know how to find the area of a rectangle, and you should be able to now think about what the area of a semicircle is. So take a little bit and try to figure out the area of this figure. All right, let's go through it. Now, there's some subtle, tricky things about this problem. One thing that isn't tricky is just figuring out the area of the rectangle, right? Maybe I'll kind of do something like this. Area of the rectangle is simply going to be that 8 inches times 10 inches or 80 square inches, right? So that's simple enough. Now to figure out the area of the semicircle, right, maybe I'll just do something like this, a semi, right, that's going to be 1/2 times pi r squared. The issue now becomes, what is the radius of my semicircle? Well, the diameter of my semicircle is that 8 inches. So the radius is simply 4 inches. Right? So we'll have 1/2 times pi times 16. Okay? Now remember, multiplication is commutative and associative. So when we've got three numbers that are multiplying each other together, and keep in mind we really do have three numbers here, 1/2, pi, and 16, we can do the 1/2 times the 16. We can do that multiplication first. Of course, 1/2 times 16 is 8. And then I'm going to just leave it like that for right now. 8 times pi. Again, 8 times pi is its own number. It's about 24, right? Because pi is about 3. But ultimately speaking now, the total area, is going to be that 80 plus 8 pi. So let's take a look at our four choices. Well, there's 80 plus 8 pi. So that's actually the correct answer. But what you want to make sure you don't do is choose this 88 pi. It would be tempting to think, oh, I got 80 plus 8 pi, so that's 88 pi. But keep in mind we don't want to do that because the 80 is not multiplying pi. We can't do the addition first and then the multiplication. These two have to stay as separate terms. So our final answer here is choice 3. All right? Again, sometimes when you're doing the area formula of a circle, you leave your answer in terms of pi, like in this problem. And sometimes, like in the last problem, you actually have to evaluate it in terms of a decimal. Okay, let me kind of step out of the way, take a look, and then we'll move on to the next problem. All right, let's do it. Shaded area problem. I love these things. Let's take a look at what it asks us to do. Exercise number 3. In the diagram below, triangle ABC is inscribed in a circle M such that AMC is a diameter. The radius of circle M is 13 and the length of BC is 24. Then determine the shaded area to the nearest whole number. All right, so I want to figure out the area that's shaded here to the nearest whole number. Okay, and the strategy should be pretty easy. Right? What I'm going to do is I'm going to figure out the area of the circle as a whole, and then I need to remove the area of the triangle. I need to subtract it out. So literally the shaded area is going to be the area of the circle minus the area of the triangle. Why don't you take a few minutes, pause the video now, and see if you can figure out both the area of the circle and the area of the triangle and subtract. Keep in mind now, you don't have to leave your answer in terms of pi because it asks us to determine the shaded area to the nearest whole number. Right? We actually want a number, a numerical answer, not in terms of pi, for this area. All right, take a few minutes. All right, well, let's work through it systematically. One thing that's not too hard to do is actually figure out the area of the circle. The reason for that is that they tell us that the radius of the circle is 13, right? So there it is. The radius of the circle is 13. So the area of the circle is as easy as just pi times 13 squared, or 169 times pi. Now I could work that out as a decimal right now, but I'm going to leave it like that for now. All right, if your instinct is to work it out as a decimal, fine, but make sure you carry a bunch of decimal places for now. Now the area of a triangle. Well, we know that the area of a triangle is 1/2 base times height. All right, and finding the area of a triangle is pretty easy if a triangle is a right triangle, because then we can use one of the legs as the base and the other leg as the height. And this is a right triangle, right? And it's a right triangle because it's a triangle that has been inscribed in a semicircle. So take us back to the last unit, right, when we did all this work with circle geometry. What we knew is that an inscribed angle, like angle B, always has a measure that is half of the intercepted arc. But angle B intercepts an arc that's 180 degrees, so this is actually a right angle. So ideally, what we'd like is we'd like to know this length and this length. Maybe the problem gave it to us. Let's take a look. Well, it tells me the radius of circle M is 13. Well, that would tell me that this length is 26, right, because it's a diameter. We know that BC is 24, but they never did give me AB. I don't have this, and I certainly can't do 24 times 26 and then divide by 2. That won't give me the area of this triangle. But because this is a right triangle, I can use the Pythagorean theorem to find the length of side AB. Maybe I'll call that just A. So this problem takes quite a bit of work, right? I mean, I have to calculate the area of a circle. I have to use the Pythagorean theorem to actually figure out a missing side of this triangle. Then I can figure out the actual area of the triangle, then do the subtraction, etc. Anyway, let's figure out that missing side. All right, we've got A squared plus 24 squared is equal to 26 squared. Remove my little random dot there. A squared plus, what would be 24 squared? It's 576. And 26 squared is 676. So, and of course, use your calculator on those. I'll get A squared is equal to 100. And what I find is that missing side that I desperately need is equal to 10. And that's going to be enough. Now that I know that that's 10, I can now calculate the area of the triangle. Let me carve out a little bit of room right here to do so. So the area now of the triangle is going to be 1/2 the base, which we'll use 24 as, times the height. We'll use 10 for that. And that is going to be 120. All right. So I've got the area of the circle, it's 169 times pi. I've got the area of the triangle, it's 120. So the area now that's shaded will be 169 pi minus 120. And again, you'll want to put this into your calculator all at once. Let's take a look. It's really quite simple, right? We just pop over to here, clear that out. We'll do 169 pi minus 120, and we find that our area 410.9, etc. Right? I think it was to the nearest square inch, so that's going to be 411. Right? Is it? Yeah, nearest whole number. 411. Yeah, and we have no units, so it's just 411. All right? And that's it. A long and involved problem, right? Hopefully the strategy makes sense, right? We calculate that shaded area by taking the overall area of the circle and subtracting the area of the triangle. Finding the area of the circle, relatively easy because we had the radius of 13, so 169 pi. Finding the area of the triangle, ironically, more difficult because we have to use the Pythagorean theorem first to find one of the legs of that right triangle. And we have to recognize it's a right triangle in the first place. But once we have it all, we can do the subtraction and be left with a final answer. All right, let's take a look at another problem. Okay, let's see what we've got here. Looks like an ice cream cone that unfortunately fell over. A shape is being designed such that it's a combination of an isosceles triangle with a semicircle whose diameter is the base of the triangle. The isosceles triangle has legs that are 10 inches in length and a vertex angle that measures 40 inches. Determine the area of the semicircle to the nearest tenth of a square inch. Show how you arrived at your answer. All right, so I'm just looking now for the area of the semicircle. I'm not actually looking for the area of the isosceles triangle. All right, but obviously one of the things that I'm missing with the semicircle is its radius. All right, so what I'd like you to do is, again, pause the video now and see if you can work through this problem and figure out the area of that semicircle. All right. Well, I'll tell you, anytime you're given some lengths and an angle, right, and you need another length, hopefully you're starting to already think about right triangle trigonometry. And in fact, what I can do in this problem is I can slice it just like that, right? And what's very, very convenient about that then is that when I carve out that right triangle, that half of an isosceles triangle, right, where I've got 10 here and I've got 20 degrees here, one of the things that's kind of awesome about it all is the length right over here, right, which corresponds to this length over there, is the radius, right? It's what I need. I'm going to actually call it r, okay? And I can use right triangle trigonometry now because r is opposite that 20 degrees and the 10 is the hypotenuse. I can use the sine. I can say the sine of 20 degrees is equal to the side opposite, r, divided by the hypotenuse, 10. Multiplying both sides by 10, I find that the radius is 10 times the sine of 20 degrees. And of course, that's what I need to calculate the area of the semicircle. Now, again, you could completely and utterly evaluate that right now, get kind of a messy decimal, write it down, store it in your calculator, do whatever you want. But I'm going to try to do it sort of all at once, because I know that the area now of my semicircle will be 1/2 pi times r squared. So that's going to be 1/2 times pi times 10 sine 20 all squared. And I can put that into my calculator. It's not that bad as long as I'm good with use of parentheses. Let's take a look. Right? 1/2 pi times 10 sine 20 squared. Right? We'll use 0.5 times pi times 10 times the sine of 20. Here's where you have to be good about parentheses. Squared. Right? There it is. Enter. And there's my final area. Now again, if you're uncomfortable with kind of doing it this way, you could easily work out what your radius is, 10 times the sine of 20 degrees, right? Like that. All right, that's my actual radius. And then you could do something like this, 0.5 times pi times my answer squared, right? It gives you the same answer, the 18.37. It's whatever you're comfortable with in terms of putting things into your calculator. Do you feel comfortable putting it in all at once? Or do you feel like you need to do something kind of in stages, like figuring out the radius here, 3.4, etc., and then kind of cranking it into the formula? Anyway, either way, 18.37, right? We want it to the nearest tenth of a square inch. So that would be 18.4 square inches. All right, check the answer sheet. Yeah, 18.4 square inches. Excellent. Take a look, and then we're going to move on and try to figure out where the area formula for a circle comes from. All right, let's move on. All right. Now again, the area formula for a circle, like many of the formulas that we look at in this unit, can only be fully derived and appreciated through the use of calculus, which is a few courses away from now, all right? But what we're going to try to do is give you kind of a sense for it in this exercise and where it comes from. So let's take a look at what we're going to be doing. Exercise number 5. Consider a circle whose radius is 0.5 inches as shown below, or right over here. Determine its circumference, half its circumference, and area to the nearest 3 decimal places. So go ahead, figure out for this circle whose radius is 0.5 inches, what its circumference is, what half of its circumference is, and what its area is to 3 decimal places. Go ahead and pause the video now and do that. All right, let's go through it. So we just did the circumference formula the other day for a circle. The circumference formula is pi times the diameter, which is also 2 pi times the radius. And this one's the one that's going to be more important for us today, all right? So it's pretty simple, you know, we just take 2 times pi times the radius, which is 0.5, all right? And we can kind of crank that into our calculators or not. Either way, accurate to 3 decimal places, the circumference is actually the value of pi, 3.142, but just accurate to 3 decimal places. Now, of course, all we have to do is take that answer, divide it by 2, and we find we get 1.571 as half the circumference. All right. Now, you may be wondering why in the world we're doing this, why did I choose 0.5, etc. I kind of did that so that we'd see the pi and the half pi there. Now, the area formula, though, right, which is what we've been looking at, is pi times 0.5 squared. And again, without, kind of going over to our calculator, let me just check what we got. We had 0.785. 0.785. All right. So where does this come from? Where does pi times r squared come from? Well, we're going to kind of explore that now using this particular circle, a circle with a radius of 0.5 inches, all right, in the next exercise. Now, there's an extra sheet that goes along with this, hopefully you've got that, where I've taken this one particular circle and I've sliced it up and I've rearranged it. And it's kind of cool. So, here I've taken the circle and I've sliced it up into 4 congruent pi slices. We're going to call them sectors of a circle. And then I kind of rearrange them so that I've got those pi pieces sort of touching like that. And I've done it again and again and again. So I've done it with 4, 6, 8. I've kept with evens each time. You could do it with an odd number, but it'd be a little bit strange, okay? And in each case, I've also given you the heights of the resulting figures and the widths of the resulting figures, all right? But again, what I still have done is essentially just carved up basically a pizza and then rearranged the slices in this particular geometric way. So, right, letter A. What must be true about the area of any of these rearrangements compared to the area of the original circle? Hopefully this is going to be straightforward, but think about that for a minute. What must be true about the areas of these rearranged figures? Well, they have to be the same as the original. They must be the same as the original. And of course, that should make common sense, right? We're not getting rid of any of the area. We're simply slicing it up and rearranging it. But yet, ultimately speaking, the area of this figure, this kind of funky figure, is still the same as the area of this because we haven't subtracted any area. We haven't thrown anything away. We've just rearranged it. And again, that's important. Now, as the number of slices or sectors increases, what does the shape of the rearrangement start to resemble? In other words, for this first one, we get this kind of cool, neat, geometric kind of pattern going on here. But as we increase the number of slices, what do these things start to look more and more like? Like especially when you look down here for that 30 slice rearrangement, essentially, what does this look like in terms of its exterior? What type of shape does that look like? Well, hopefully, you said parallelogram. Maybe even you said a rectangle, which is a type of parallelogram, right? It's looking more and more like a parallelogram, right? In fact, even by the time we hit 8 slices right here, it looks relatively like a parallelogram, just with, some like little bumps on top of it. And by the time we're at 30 slices, if I just simply outlined this thing and I said, what is that? I would hope everyone would say, yeah, it's a parallelogram, right? Now, letter C. What value does the height of the rearrangement continue to get closer to? What does the base length get closer to? All right? And in fact, we can really take a look at that by looking at what we would get if we carved it up into 100 pieces, 200 pieces, 500 pieces, 1,000 pieces, 2,000 pieces. Take a look. Right here on that bottom row are the heights. The height of that overall figure at 100 pieces is 0.5003, at 200, 0.50006, etc. What is that height getting closer to? Well, it's getting closer to the radius of the circle, right? And what is the width of that figure getting closer and closer to? 1.5862, 1.5786, 1.5739, etc. That thing is getting closer and closer to, and this is a little bit harder to see, it's getting closer and closer to half the circumference. All right, so let's fill those in. Okay, the height is getting closer and closer to the radius, and the width is getting closer and closer to 1/2 of the circumference. All right, now remember, the figure itself, right, is getting closer and closer to a parallelogram / rectangle, right? In fact, if we had something at 10,000 slices and then rearranged them, they'd be very, very thin slices. But it would basically look indistinguishable from a rectangle. A rectangle whose height is the radius of the circle and whose width, or base, is 1/2 the circumference. Now it says, what does the value of the area of this new shape approach? Well, we can calculate the area of a rectangle / parallelogram by simply taking its height and multiplying it by its base, right? So in fact, if I just did that particular, calculation, 1.57096, and I multiplied it by 0.5000, how many zeros are there? 1, 2, 3, 4, 5, 6. 5, 6, 2. If I did that, what I would find is I would find an area of about 0.785, right? I would find the area of the circle, which is interesting because in this calculation, when I'm multiplying this width by this height, of course, I'm doing the area of a rectangle, right? Or the area of a parallelogram, same area formula. And yet, I'm getting the area of my circle, which makes sense because overall, right, the area should remain the same, no matter how we slice this thing up. So what are we really getting at? Let's go kind of more general. Right here, we had been using a radius of 0.5, now let's use a radius of just r. Well, if you think about this, right, if this can be extended, and we've chopped up, a circle with a radius of r instead of 0.5, then as we chop it up into an infinite number of slices that are very thin, the height of that rectangle or parallelogram gets very close to the radius. It approaches r, the radius of the circle. The width, on the other hand, approaches 1/2 the circumference. But what would 1/2 the circumference be? Well, the circumference, right, is 2 pi times r, right? So if we do 1/2 times 2 and just let those cancel, then the width just becomes pi times the radius. And now everything is shifting on me. Oops. All right, so in general, right, if we take a circle with a radius of r, we slice it up into an infinite number of slices and then we kind of rearrange them, then we're going to get a rectangle whose height is r and whose width is pi times r. So what's its area? Well, its area will be pi times r, so its area will be pi times r squared. And that's where the area formula for a circle comes from, at least from the context that we can see. Let's take a look at this actually in GeoGebra. It's, if you don't mind me saying, wicked cool, right? Here we've got a circle, okay, with a radius of r. All right, and what I'm going to do is I'm going to straighten out the circumference. All right, so there's my circumference. All right, 2 pi times the radius. Now what I'm going to do is I'm going to dissect the thing. Okay, just like we did before. And what we can do, hopefully, is we can rearrange that thing, right? There I've kind of like made all the pi pieces kind of flip out like that, and then they come back together. Now again, what we've got here really is we've just simply got a parallelogram whose height is roughly the radius and whose width is 1/2 the circumference, all right? And as we increase the number of slices, right, what we get is we get a figure that looks more and more like a rectangle whose height is r and whose base is pi times r, 1/2 the circumference. So the area now of this rectangle simply becomes, right, pi times r, or pi times r squared. It's weird, because circles don't seem like they have a lot to do with rectangles, and yet we can get at the area formula of a circle if we know the circumference formula for a circle, and we know how to slice it up and rearrange it into this sort of parallelogram / rectangle-like shape. All right. You'll be able to see more in terms of how the area formula for a circle kind of comes up if you go on and take calculus at some point. All right. So in this lesson, what did we do? Well, first, we reviewed the area formula for a circle, and then we used it in a variety of different ways that necessitated that we use other skills from this course, including looking at the equation of a circle in order to identify its radius, so we could just calculate its area, and things like that shaded area problem where we had to use the fact that we knew that that triangle was a right triangle given that it was inscribed in a semicircle. All right. Now the last piece of this lesson really got at where does the area formula for a circle come from. Now again, you don't necessarily have to totally understand that, but it is something that at this point you have enough tools to kind of like visualize and see so that that area formula of pi r squared isn't a total and complete mystery to you. All right. Well, again, more understanding will come later if you stick with math all the way through calculus. For now, though, I'd like to just thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.